You step outside in the morning. The sun is up, coffee in hand, everything is completely normal. Then you notice something wrong with the sky. There's a second sun, slightly smaller, slightly bluer, rising in a different part of the sky, at a different angle, casting a second shadow at your feet that points the wrong direction. The grass looks strange, lit from two sides at once, like a stage under twin spotlights. You are no longer in the solar system. Earth has been moved. And depending on where we dropped it, what comes next is either fascinating, terrifying, or actively trying to kill every living thing on the surface. Today, we are running the experiment. 4 star systems, each one more violent than the last. Same planet, different neighborhood. Let's find out how long you last and why the solar system might be the luckiest address in the galaxy.
The most common type of star system in the galaxy is not a single star with a family of planets orbiting it. It is 2 stars orbiting each other. Roughly half of all sun-like stars exist in binary pairs, and the nearest star system to Earth, Alpha Centauri, is one of them. 2 stars, Alpha Centauri A and B, orbiting a shared center of mass roughly 23 AU apart, about the distance from the Sun to Uranus, give or take. We are dropping Earth into this system, into what astronomers call a circumbinary orbit, a path that goes around both stars simultaneously, far enough out that the combined gravitational field of both suns looks, from Earth's perspective, roughly like one big source of light. This is the optimistic version of the binary swap. Let's see what it actually does to you.
The first thing that changes is the calendar. Earth's year, the time it takes to complete one orbit, would shift dramatically depending on the distance we place it from the binary pair. But here is the stranger effect. As the 2 stars orbit each other on their 80-year cycle, the amount of radiation reaching Earth changes. Some years, both suns are on the same side, pointing at Earth together. The combined output increases. The average global temperature edges upward. Ice caps shrink. Then, the stars shift to opposite sides of their orbit, and the radiation balance changes again. Earth experiences climate cycles tied not to its own axial tilt, but to the slow dance of 2 stars that neither notice nor care about it.
The second problem is the seasons. In the solar system, seasons exist because Earth is tilted 23.5 degrees relative to its orbital plane. This means different hemispheres receive sunlight at different angles throughout the year. In a binary system, you now have 2 sources of solar radiation at different angles, and they move relative to each other. The shadow geometry becomes strange. Near the summer solstice, one sun might be high overhead while the other is setting. The sky is never fully dark. In the polar regions, there are periods of weeks where the planet receives continuous radiation from at least one star at all times. And at the same time, in the gaps between the 2 suns' positions, you get brief periods of something like a double sunset, both stars visible on the horizon simultaneously before everything shifts again. The long-term result? A planet with a climate that is permanently unsettled. Not destroyed, not even necessarily uninhabitable, but never stable enough to develop the multi-million-year stretches of moderate conditions that allowed complex life to emerge on Earth. Microbes, probably. Trees, maybe. Civilizations built on agriculture that requires predictable seasons? That is where binary stars make things genuinely hard. But compared to what comes next, 2 suns is practically relaxing.
A neutron star is what remains after a star between 8 and 20 solar masses exhausts its fuel and collapses. The outer layers explode outward in a supernova. What is left at the center is an object roughly 20 kilometers across, about the size of a city, but with a mass between 1.4 and 2.1 times that of the entire Sun. The density is so extreme that a single teaspoon of neutron star material would weigh approximately 10 million tons on Earth. The gravity at the surface is 2 billion times stronger than what you feel standing on this planet. We are placing Earth in orbit around PSR J0437-4715, a neutron star 520 light-years from Earth that is also a pulsar, meaning it rotates at high speed and emits 2 beams of electromagnetic radiation from its magnetic poles, sweeping through space like a lighthouse. This particular pulsar rotates 174 times per second. The beams are not visible light, they are X-rays and gamma rays.
At the distance we are placing Earth, roughly 1 AU, the same distance as from the Sun, the neutron star provides almost no warmth. It is a cooling object, not a burning one. The surface temperature of a young neutron star is around 1,000,000 degrees Celsius, but it radiates primarily in X-rays, not visible light. A world orbiting a neutron star at 1 AU would receive virtually zero usable solar energy in the wavelengths that drive photosynthesis. The planet would be cold, perpetually lit by X-ray pulses 174 times per second, like a strobe light made of radiation, but essentially dark in the wavelengths that plants, eyes, and solar cells use.
But the real danger is not the daily radiation dose. It is the periodic events. Neutron stars are not calm. Many of them experience what are called magnetar flares, sudden releases of energy caused by starquakes in the crust, events where the rigid outer layer cracks under the stress of the magnetic field. The strongest of these, observed from a magnetar called SGR 180620 in 2004, released more energy in 0.2 seconds than our Sun emits in 250,000 years. The flare was detectable from Earth at a distance of 50,000 light-years and briefly disrupted the ionosphere. Our planet was not in its path. If it had been, and at close range, the ozone layer would have been stripped away within minutes.
For Earth orbiting a pulsar, the threat is a matter of when, not if. The magnetic field evolves, crust stress builds up over thousands of years. Then, without warning, one event. Not a constant burn, but a pulse. A single burst of radiation at close range that ionizes the upper atmosphere, dissociates ozone molecules faster than any natural process can replace them, and leaves the surface exposed to the full ultraviolet output of whatever other stars exist nearby, and to cosmic radiation the atmosphere previously blocked. Life on the surface does not necessarily die in the event. It starts dying in the years that follow as the UV flood continues. But even a neutron star's worst day cannot match what the third system does on a perfectly ordinary Tuesday. Everything we have looked at so far has involved a star that is, in some sense, just existing in an inconvenient way. A binary star that creates unpredictable seasons. A neutron star that periodically emits lethal radiation. Dangerous, yes, but none of them are actively trying to destroy the space around them every single moment. WR-104 is a Wolf-Rayet star located 8,000 light-years from Earth. Wolf-Rayet stars are massive, typically 10 to 20 times the mass of the Sun, and they are dying. A Wolf-Rayet star is one that has burned through its hydrogen reserves and is now blasting its own outer layers into space at speeds of up to 2,000 kilometers per second. Our Sun produces a solar wind of roughly 500 kilometers per second, with a mass loss rate of about 1/1,000,000th of the Earth's mass per year. A Wolf-Rayet star loses the equivalent of Earth's entire mass every 10,000 years, continuously in every direction at supersonic speeds. We are placing Earth into orbit around WR-104 at the same distance as Venus orbits our Sun, close enough to receive comparable warmth, close enough to sit inside the outflow zone. The first consequence is the atmosphere. Earth's atmosphere is held in place by gravity and protected from erosion by the magnetic field, which deflects the solar wind. Against a Wolf-Rayet stellar wind, the magnetic field is not enough. The pressure of the outflow at this distance would exceed the magnetic field's containment capacity. The atmosphere does not disappear instantly. It erodes. Lighter gases go first, hydrogen from water vapor, then nitrogen, then oxygen. The process takes thousands to tens of thousands of years. For a planet, that is almost nothing. The surface pressure drops. Temperatures swing wildly without the greenhouse blanket. Water boils off into space. But the more immediate problem is radiation. Wolf-Rayet stars are among the brightest objects in the galaxy in the ultraviolet and X-ray spectrum. The UV output of WR-104 at the distance we have placed Earth would be roughly 100,000 times what Earth currently receives from the Sun. At that level, the ozone layer does not just deplete, it was never stable to begin with. The surface receives UV radiation that would denature proteins and break DNA strands faster than any repair mechanism could correct. Not on evolutionary timescales, on years to decades timescales.
And then, at some point, no one knows when, it could be tomorrow in astronomical terms or 1,000,000 years from now, WR-104 will produce a gamma-ray burst. A Wolf-Rayet star's final act is a hypernova, a collapse so extreme that two jets of gamma radiation are fired outward along the polar axis at nearly the speed of light, carrying more energy than the sun will emit across its entire 10 billion-year lifetime. WR-104 is believed to be one of the most likely nearby candidates for a gamma-ray burst that could affect Earth. From 8,000 light-years away, the burst would deliver enough gamma radiation to destroy the ozone layer and likely trigger a mass extinction. From the distance we have placed Earth in this scenario, the burst would not just strip the ozone, it would sterilize the surface down to the bedrock in under a minute. But even this is not the most extreme thing we can do to a planet.
The solar system currently sits about 26,000 light-years from the center of the Milky Way. This is not an accident. The galactic center is, by any measure, the most violent environment in the galaxy. We are placing Earth there. Not into a black hole. That would end this video in one sentence. We are placing Earth into orbit around a star in the S cluster, a group of massive stars that orbit Sagittarius A star, the Milky Way's central supermassive black hole, at distances ranging from about 1,000 to 10,000 AU. These are stars that complete a full orbit around a 4 million solar mass black hole in as little as 16 years. The first problem is the stellar density. Out here, the nearest star to the Sun is Proxima Centauri, 4.2 light-years away. Near the galactic center, the average distance between stars is less than 0.1 light-years. In some regions, it drops below 0.01 light-years, roughly 1,000 times the distance from Earth to the Sun. At that density, gravitational encounters between star systems happen on timescales of millions of years rather than billions. A planet that has managed to stay in a stable orbit around its star is playing a game with far shorter odds than anything in the outer galaxy. The gravitational nudge from a passing star is not a once-in-a-solar-system event. It happens repeatedly. The orbit shifts. Over time, a planet in the S cluster experiences what Earth experiences in a binary system, amplified by orders of magnitude and repeated throughout its history.
The second problem is Sagittarius A star itself. A supermassive black hole does not just sit there, it eats. When gas, dust, or stellar material falls into the accretion disk around SGA star, the material heats up to billions of degrees and releases X-rays in massive bursts. SGA star is currently considered relatively quiet, in a dormant phase. Even in this quiet phase, it produces X-ray flares many times per day. In active phases, which astronomers believe have occurred multiple times in the galaxy's history, most recently about 3.5 million years ago, when it produced the Fermi bubbles, two lobes of high-energy gas extending 25,000 light-years above and below the galactic plane, the radiation output increases dramatically. A planet in the S cluster during an active phase of SGA star receives X-ray doses that dwarf anything a Wolf-Rayet star produces in daily operation.
There is also the issue of stellar flyby supernovae. Near the galactic center, massive stars have short lives. They form fast, burn fast, and explode fast. The rate of supernova events there is higher than anywhere else in the galaxy. A supernova within 30 light-years is a potential extinction-level event. Near the galactic center, the interval between such a close-range blast drops from hundreds of millions of years to something far shorter and far more likely than where we live. A planet in this central cluster isn't waiting for one bad event. It is a world being continuously carved by radiation, gravitational chaos, and proximity to the galaxy's most energetic objects. The most optimistic model for life here isn't multicellular or even complex single-celled. It's whether any chemistry stable enough to reproduce can exist where the rules are rewritten every few million years, and where, at any moment, the black hole at the center of everything might decide it is hungry again. Here is what this experiment reveals once you run it to completion. The solar system is not just a collection of planets. It is a location. And location, in the galaxy, turns out to matter enormously, in ways we almost never think about. The Sun is a G-type main sequence star, stable, consistent, non-violent. It has been producing almost exactly the same amount of energy for 4.6 billion years, varying by less than 0.1% per century. It does not have a companion star pulling on Earth's orbit. It is not a pulsar sweeping lethal beams across the system 174 times per second. It is not a Wolf-Rayet star blasting its own surface into space. And it is 26,000 light-years from the most violent neighborhood in the galaxy.
We exist in what some astronomers call the Galactic Habitable Zone, a ring-shaped region of the Milky Way, roughly 23,000 to 30,000 light-years from the galactic center, where stars are old enough to have produced heavy elements, where the radiation environment is calm enough that complex chemistry can persist across billions of years, and where supernova rates are low enough that the surface of a rocky planet has a reasonable chance of staying intact. Move inward toward the galactic center, and the violence increases with every light year. We did not choose this address. We are here because the physics of the galaxy 4 billion years ago produced a star in this particular location, around which a rocky planet settled into an orbit that stayed stable for long enough for the molecules on its surface to start copying themselves. The probability of each step was not 0, but it was not high either.
The next time you look up at the sky and see only one sun, in the same position it was yesterday and the day before, and every day for as far back as any human record reaches, that is not boring. That is the specific, improbable quiet that makes everything else possible. Somewhere in this galaxy, right now, there is a planet exactly like this one, orbiting a Wolf-Rayet star in the final years before the burst. Its end will be a supernova, an explosion that will scour its surface instantly. It does not know that, and neither, until today, did you.